Good afternoon, everyone. My name is Vamsie. I'm a thermal analysis engineer from American Battery Solutions. So in this presentation, I'll be talking about like co-simulation between GT Suite and Simulink and how it helped us, reduce the test timings and how seamlessly it co-simulated. It is more like an user experience presentation. So let's see the agenda first. So I'll be talking about American Battery Solutions, introduce our organization to you. And after that, I'll be talking about the problem statement and the case setup, why we co-simulated GT Suite with MATLAB Simulink. And after that, we'll talk about the results and implications. And finally, what we are planning to do in the future using GT Suite and the other tools. First up, we are American Battery Solutions, battery pack manufacturers, founded in 2018. We are an young organization, but rapidly growing into one of the biggest battery pack manufacturers in North America. We acquired a ready-to-scale facility back in 2018, and we produced almost like 60,000 battery packs from that facility. We are a team of like 250 people with 90 engineers dedicated for like battery pack manufacturing. We are also ISO 9000 certified. We got that certification back in 2022. And our area of expertise is module production, battery and thermal management, pack assembly, but we also have engineers who are experts in cell technology and integration of the pack. So our target market is the underserved market in various segments like delivery trucks, buses, utility vehicles, rail and marine, high-performance vehicle and autonomous vehicle in transportation, and material handling equipments, construction, agricultural, and mining equipments in industrial, as well as ESS and distributed energy resources in commercial segment. So now jumping into the main part of the presentation, which is what is the purpose of this study which I'm presenting. So at American Battery Solutions, we manufacture packs which must perform at extreme geographical as well as weather conditions. So BMS plays a very important role in like maintaining the cell temperatures within an optimal limit, which is safer to operate. In this presentation, particularly, I'll be talking about the thermal limits and how BMS maintains the cell at those thermal limits. And for this analysis, we used co-simulation with MATLAB and Simulink. And why we used is because the co-simulation was actually faster, cheaper, and we were able to test multiple different scenarios without any issues, and it's seamlessly integrated. And first, I'll be talking about like the signal description, how the co-simulation was set up. The initial conditions, like the initial temperature, ambient temperature, the flow rate, and then the heater power available were all fed into like the MATLAB Simulink, which hosts the heater or cooling control logic, and then to the thermal system model, which is GT Suite. And the first run, GT Suite runs with the initial condition and feeds the cell temperature, like the maximum temperature, minimum temperature, average temperature, as well as the coolant temperature to the MATLAB Simulink model. The MATLAB Simulink model, based on all this information from the thermal model, decides what thermal mode. Thermal mode is something like whether it should be in the heating mode, cooling mode, or the balanced mode. So the MATLAB Simulink model feeds back the thermal model with the thermal mode, flow rate required, and the heating and cooling rate required. And to your right is the GT Suite model. And this model is correlated, which I'll be talking about in a few slides. And the GT Suite thermal model was integrated into MATLAB Simulink environment. As you can see, this slide is just a visual representation of how it was integrated. The GT Suite, just a second. Yeah, sorry. The GT Suite is at the center here, and then these signals are from Simulink to GT Suite, and then these are the signals from GT Suite to Simulink, and it is actually in loop. So it is a real-time co-simulation where it gets feedbacks and runs the thermal model in parallel with the BMS software. So I was talking about thermal modes a lot. So this slide is just a small representation of what the thermal mode means. This is not the actual thermal mode. This is just a representation. So the thermal mode, we have like 5 different modes. The first one is 0, which is initial condition. And then number 1, which is heating mode. Number 2 is balance mode, which is to maintain the cells at the limit which is already there. And the third one is cooling mode. And the last one is max cooling mode. So based on what the MATLAB Simulink or the thermal software reports, the GT suite must operate on that mode. And how we did it? By integrating multiple switch-based logic control. So GT suite gets the thermal mode from the MATLAB and Simulink, and based on the mode, it heats or cools down based on the switch logic, which is explained in this slide. So we use a S-block GT Simulink bridge in order to get all the information. It acts like a portal which transfers information from GT suite to MATLAB Simulink and from MATLAB Simulink to GT. So we get 3 informations, the heating rate, cooling rate, and then the thermal mode. So we calculate both the cooling rate and the heating rate in parallel initially based on the tables shown here. So based on the temperature, the coolant power either increases or decreases, and based on the cell temperature, the heater rate increases or decreases. So this table is for a wide range of temperature based on the application. And all the 3 information, like the cooling rate, heating rate, as well as the mode, goes to the master switch. And the master switch decides which signal to pass on based on the thermal mode. And on your right is just the visual representation of how the logic was implemented in GT suite. And before testing software with GT suite, we know that it's a very huge step. So we took precautionary measures by running various different correlations of the thermal model. We ran steady state correlation, transient correlation, flow correlation, using test data, which we tested in-house. And few information like the flow distribution in cold plates is very hard to get in test data. So we relied on CFD data in those, for those information. And the CFD model is correlated as well. So as you can see on the left side plot in this slide, the transient data is correlating very well. And then the flow distribution is also well within 1% from the CFD results. Next up, these are the cases which we tested using this co-simulation methodology. We ran a wide variety of tests, but not just limited to these 7. These are just representation, where we soaked the vehicle at extreme cold weather condition like negative 29 degrees Celsius to like extreme hot weather like 41 degrees Celsius. We ran different scenarios like overnight soaking, turning on the vehicle in the morning, and then like preconditioned cells, not preconditioned cells for like a couple of hours, and then ambient condition, everything. And just for the sake of time constraint, we'll be discussing about 2 cases in this presentation. The first one is cold weather warm-up, where the vehicle is soaked in cold weather, and then the vehicle is operated in the morning. So it starts off at like negative 5 degrees, and then the BMS senses that the battery temperature is negative 5, and then it sends the heating mode signal to it, which is the green line here. First, it is in the heating mode, and then once it reaches the optimal temperature lower limit. So let me tell about this optimal temperature limits. Like I said in the earlier slide, the batteries must always be in the optimal temperature zone in order for it to operate safely and efficiently. So that is the lower limit and then the upper limit. The purpose of BMS is to maintain the cell temperatures within this limit. So once it reaches the optimal temperature lower limit, the battery mode moves from heating to like the balancing mode. But since the vehicle is still running and there is heat generation in the cells, the cell temperature keeps increasing, and we wanted to test the software, so we had a sudden burst of heat release It is kind of designed, I don't mean to say it happens in real life, it is just for like testing the software purpose. We increase the cell temperature to see how the software responds. So as it senses the temperature of the cells increasing, it moves to the cooling zone and tries to cool the cells down and bring it back to the optimal temperature zone. Next up is the hot weather condition, where the ambient temperature and the initial temperature are at 41 degrees Celsius. So the BMS requests the pack to be cooled initially, so the temperature of the cells starts to cool down, and once it reaches the optimal temperature upper limit, it goes into the balancing mode. By just varying the flow rates, it is trying to optimize the cell temperature. But this is where we found the issue highlighted here in the red circle. We saw that the flow rate was like fluctuating up and down, like the BMS was requesting a flow rate which was fluctuating in a very short period of time. So the main purpose of these kind of testing is to identify these issues and then rectify it before testing it in the actual actual model. So we were able to identify it and rectify it. So finally, what are we planning to do with GT Suite and the other tools in the future? We are planning to develop a thermal runaway prediction model using GT Suite, and then an electrical equivalent model to test the electrical circuits. And the third one is pack level aging analysis. If you attended last year's GT conference, I presented about the aging models. We did cell level aging, calendar life, cycle life, as well as like OCV correlations, which was successful. And the plan is to like do a pack level aging model and integrate it with thermal model in the near future. And finally, to develop a simulation ecosystem where all the analysis tools co-simulate with just one single input, where the thermal model, the controls like the MATLAB and Simulink and everything is in a single environment.